I will be talking about the complexity of the homeomorphism equivalence, some subclasses of compact metrizable spaces. Okay, this is a joint work with Pavel Krupsky from last year, and well, I was told that I don't need actually to explain too much detail about the notion of Borel reducibility, because I know that there are several experts on that topic. But anyway, I will tell at least the main definitions. Okay, so the topic is complexity of the homeomorphism equivalence relation. Okay, so first of all, I will just give the definition of Borel reducibility. Perhaps I don't need to explain why this notion is useful for comparing complexities between some structures. Okay, so definition is as follows. So suppose that X and Y are Polish spaces and E, respectively F, are equivalence relations. Well, in our cases, these E and F will be usually analytic, or they will be always analytic. Okay, and we say that E is Borel reducible to F and we just write simply E is less than or equal to F if there exists a Borel mapping F from X to Y such that whenever we take X and X prime in X, then it holds that X is E equivalent with X prime if and only if f of X is F equivalent to F of X prime. And we say that E is Borel bireducible to F and we write E is Borel bireducible to F and vice versa. Okay, so in our cases, X and Y will be some collections of structures, and these equivalence relations will be some kind of isomorphisms between these structures, or homeomorphisms, or whatever. Okay, so I should just know that here X and Y are supposed to be Polish spaces. Of course, it will be enough that X and Y are just standard Borel spaces, but if you don't know what a standard Borel space is, then maybe this is better. Sometimes we will be also dealing with continuous reducibility, so then this function f is supposed to be continuous But mainly we will be dealing with Borel reducibility. Okay. So I can just note that the most basic equivalence relations are ordered by this in the following way. Well, if we consider an equivalence relation that has only one equivalence class, then of course all these are Borel bireducible, and this is Borel reducible to the equality on two elements and so on. Then we can consider the equality on a countable set. All of these are Borel reducible into that. This is Borel reducible into the equality on real numbers. Okay, all of these equivalence relations are called smooth. And okay, I should just end with some, well, maybe the first somehow non-trivial. Say the Vitali equivalence relation that is defined in that way that, so the Vitali equivalence relation is a relation on real numbers, and x and y, or x and x prime, are equivalent if and only if their difference is a rational number. Okay, so in the theory a lot of is known. I do not know too much here, but I will be mainly interested in some applications in topology, and in order to formulate our results, I need to define two outstanding equivalence relations. Okay. But maybe before doing that, I can give just a simple example. Just to motivate the type of result that we are seeking for. So Gromov proved that there exists a Borel mapping F going from all compact spaces, compact metrizable spaces, or sorry, compact metric spaces to real numbers, such that if we take two metric spaces, say K and L, then K is isometric to L if and only if f of K is equal to f of L.
Can you say a word about why this is a Polish space?
Yes, of course. So this is not, of course, not a correct statement, because this is just a proper class, all metric spaces. But this is usually the case that the results are formulated somehow roughly, and we need to specify how the objects here, how they are coded. Usually there are several ways how we can code those objects into a Polish space. So for example here, we can consider compact metric spaces as subspaces of the Horizon universal space. That is a Polish metric space that contains isometric copy of every separable metric space. Okay, and we can consider this horizontal universal space and the hyperspace of all compact subsets. And this give us a Polish thing that is in fact coding all compact metric spaces up to isometry.
What's the distance between two compact subsets?
Well, we can take the Vietoris topology there, or the Hausdorff metric.
Oh, I see. That's
Okay.
okay.
But there are another natural ways how to code this proper class. We can consider.
But a metric space is not just the space; it's the metric as well.
Yes. There is another natural way how to code this. So we can consider the metrics restricted to some countable dense subsets. Okay, because if we make a completion of that metric restricted to a countable dense subset, we will get the original space up to isometry. So there is another way how to code this by considering all metrics from n times n to R such that rho is a totally bounded metric. So this can serve as an alternative coding of this, and there is a natural topology that is obtained as a restriction of R to n times n. And this is a Polish space, right? It turns out that these two codings are compatible. Okay, we get the same result for them. And it is usually this case that we have several types of coding, but as I know, the results are always the same. I don't know whether there is some theorem behind or something hidden in logic, but usually it works well. And this is why all this theory is works well. Okay. Okay, so here, of course.
Are you saying it's a closed subspace of this product?
Well, definitely it's G delta, this one. Yeah. So then it is a Polish subspace. Mm-hmm. Okay. So a lot of examples of analytic equivalence relations of Polish spaces arise from continuous actions of a Polish group on a Polish space. Okay, so if we suppose that G is a Polish group, and X a Polish space, and A is some action of G on X, a continuous action. Then we can consider the equivalence relation on X as all the orbits that are given by this action. So we can define this equivalence relation, say EA, that is defined as all the pairs X and X prime such that there exists some g in G for which gx equals x prime. Okay, and this is called an equivalence that is induced by that group action A. Well, so for example, as I was talking about this Vitali equivalence relation, so this is obtained in this way. We can consider the discrete group of rational numbers. This acts on real numbers by addition, and the orbits are actually the equivalence classes there. Okay. For my purposes, I need to describe two outstanding equivalence relations, well, up to Borel by reducibility, and they can be described by the following fact. So if we consider some fixed group, G, then if we consider all the actions of G on some Polish space and all the corresponding equivalence relations, there exist in this class of equivalence relations EA, where A is an action, is a continuous action of G on some Polish space X. So here there exists the biggest element with respect to this quasi-order of Borel. Okay, so this is just a fact. I don't remember who proved that. And it will be especially important for us if we consider the group.
Isn't there a stronger statement? So the action is universal, not just the orbit relation.
Yes.
As a consequence, the orbit relation.
Yeah, so I am writing it in a minimal way that I just wrote what I will need. Okay, so especially if we consider the group G to be the Polish group of all permutations of a countable set, we will denote the biggest element of this by E as infinity. Okay, I don't actually know whether there is some standard notation for that, but I saw that one and it seems to be quite good. Okay, if we consider here the universal Polish group that exists by a result of Uspański, then we get we denote it by E G infinity. Okay, but maybe this is not so important because we can think about these equivalence relations in some other and maybe more comfortable way. And this follows by the following remarks. Well, it is known that this equivalence relation E as infinity is Borel bireducible with several equivalence relations. One of them is the isomorphism relation of countable graphs. Isomorphism equivalence relation of countable graphs. Okay, so we consider all graphs on a fixed countable set. This forms a Polish space, and we consider isomorphism equivalence relation on this Polish space. And this one is Borel bireducible with that one. Also, it is true that this is Borel bireducible to isomorphism equivalence relation of countable linear orders. So again, we consider a fixed countable set, like the natural numbers, and we consider all linear orders of that countable set. So these are binary relations. Again, this forms a Polish space with a natural topology. And if we consider isomorphism equivalence relation on that space, then this one is Borel bireducible to this E as infinity. Okay, so no matter what E as infinity is, it is something as complicated as this or this. Okay, and similarly, there are some results for this EG infinity. This one was shown to be Borel bireducible, for example, to isometry equivalence relation of Polish metric spaces. Again, this can be coded in several ways. Either we can consider the Urizon universal space and its closed subspaces with the Borel-Efro structure, or we can consider all the metrics on a countable set and identify these metrics with the completions. Okay. Or there is another result that this is Borel bireducible to linear isometries, linear isometry equivalence relation of separable Banach spaces. Okay, so I presented these results just for the feeling how complex these equivalence relations are. Okay.
I mean, they're different, right?
Yes, they are different, and okay, yes, this is what I should also point out, that of course ES infinity is Borel reducible to EG infinity, but it is strict here, so one cannot Borel reduce this one into that one.
Why is that? How do you show that it's strict?
Well, this follows from the turbulence theory. Am I right? Yeah.
Oh, you have to produce a non-turbulent action.
Yes.
Turbulent action.
Yeah. Mm-hmm.
It's always true that if you have one subgroup of another, then the relation for the smaller group is Borel below for the bigger one.
Okay, now I'm not completely sure about that. Okay, I'm not completely sure. Maybe somebody knows. Correct answer.
Yes, if you have one polar subgroup of another, then relation to smaller relation to bigger is always Borel below.
Maybe if the smaller group it could be as a homomorphism image of this bigger group, then
Well, I'm not saying strictly, but just in case you say they will be just the same. Never mind, it's just a relation.
Mm-hmm.
Did you solve loss rejection or something?
No, something much
Just curious.
Okay, so now let us denote by H the homeomorphism equivalence relation.
On what?
I'm not specifying.
Okay, seems very broad.
Yes, but compact metrizable spaces will be enough, and I will then restrict to some smaller classes.
Okay. So in most compact metrizable.
Yes. So it is a result of Zielinski from 2016 that this EG infinity is Borel bireducible to the homeomorphism equivalence relation on compact metrizable spaces. Again, I should say what is the coding here. Well, every compact metrizable spaces can be embedded into the Hilbert cube. So we can consider the Hilbert cube and the hyperspace of all compact subspaces. The hyperspace with the Vietoris topology or Hausdorff distance, and it is a compact space even. So it is a Polish space. So this is a very natural way how to code all compact metrizable spaces.
And make sure it's a Gromov isometry.
Yes, these were isometries. It is smooth.
The homeomorphism is much.
Yeah. Okay. 1 year later, Chang and Gao proved that if we restrict this relation to a smaller set, just to continua, so connected compact metrizable spaces, then this is still Borel bi-reducible. Okay. Of course, if we take smaller class, the Borel reduction from this side to that side is simpler because it is given just by inclusion, because we can assign to every continuum a compact space. But the other direction is not so easy. Okay. Later on, Češla proved that this is Borel bi-reducible to the homeomorphism equivalence relation restricted to even smaller class of locally connected continua. So these are continua having a base from connected subsets. Okay. And when we started dealing with that question, we were able to restrict this even to up. So we proved that these compact metrizable spaces are Borel bi-reducible to the homeomorphism equivalence relation when restricted to absolute retracts. Okay, I should write the so an absolute retract, or shortly just AR, can be described as a retract of the Hilbert cube. Okay, of course there are inclusions. This is the biggest class, this is smaller, this is even smaller, and this is even smaller than that one. Okay, but still the complexity of the homeomorphism equivalence relation is still the same. Okay, on the other hand, there were some results that the homeomorphism equivalence relation on some really small classes of compact spaces is Borel bi-reducible to this ES infinity. So this was proved by Camerlo, Darci, and Marcone. That this ES infinity is Borel bi-reducible to the homeomorphism equivalence relation when restricted to so-called dendrites. And a dendrite, this is by the definition a locally connected continuum not containing a simple closed curve, so not containing a subspace homeomorphic to the circle. This is in fact equivalent to be one-dimensional absolute retract. Okay, so since this ES infinity is, for me, it's the complexity of isomorphism between countable structures. So from some point of view, dendrites and homeomorphisms between them behave in a similar way as isomorphisms between countable structures. Okay, we were trying here to enlarge this class, still to have Borel bireducibility here, and we were able to prove that this is Borel bireducible to the homeomorphism equivalence relation restricted to so-called rim-finite continua. Well, being rim-finite means to have a base such that the boundaries are finite.
Did you invent rim-finite, or did that already exist?
Sorry?
I'm trying to understand where these notions came from. So this notion of
no, it exists.
there's this study of continua, and they
Well, not only in continua, but also in general topology, these rim-finite, rim-countable, or rim-compact spaces. For example, rim-compact means that there is a base such that the boundaries are compact. Okay, so these classes are somehow studied, and well, it follows actually that every dendrite is a rim-finite continuum. Okay, maybe I could draw some pictures, so how a dendrite could look like. So for example, if you take a finite tree, combinatorial tree, you can very naturally put a topology on that, right? And then it is a dendrite. But there are more complex dendrites. So for example, if you consider this picture, a countable union of arcs such that the diameter tends to 0, this is a dendrite, okay? If you consider an arc and you attach to some countable dense subsets smaller and smaller arcs, what you get is a dendrite again, okay? Or there are, for example, universal dendrites that can be constructed in such a way that you are attaching on the longest free arc every time. Okay, and finally you take the union. You have to be quite careful so that if you take the closure, you didn't create a circle there, and you get some kind of universal dendrite then. Okay, but rim-finite continua, this is much larger class than this one. For example, if you consider the Sierpinski triangle, so you consider the full triangle and you erase the interior of that triangle, of these triangles, and so on. So you consider the intersection, then this is a compact subspace of the plane. And it is in fact in fact a infinite continuum, because you can consider like these sets. Well, it has a finite boundary, just these 2 points. Okay, so these triangles, the boundaries have usually at most 3 points. So this is an infinite continuum, but it is of course not a dendrite because there is a lot of circles in there. Okay, so what we were able to do, we were a continuum and we code it as a countable structure, because it is known that actually if we take any countable language and we consider the structures on a countable set, then the isomorphism relation between these structures is Borel reducible to this ES infinity.
Can you give an example of something like this, but that's rim countable and not rim finite?
Rim countable and not rim finite? Well, for example, if you consider like the harmonic fan, a fixed arc and a countable sequence of arc converging to it. So it is rim countable but not rim finite.
Okay. You don't have any results about rim countable?
No, we don't have. Okay, there is another.
Your conjecture, rim countable should go up to the universal.
Well, we don't know. We don't know actually. In a few minutes, I will present some questions.
It made me feel like your intuition is that if it's reducible to S infinity, then it's classifiable.
Yes.
And otherwise, not. So you're going to tell us something in between?
Yes, we have something. Or precisely. Some more result concerning this ES infinity was given by Camerlo and Gao. 2001, that if we consider homeomorphism equivalence relation restricted to zero-dimensional compact metrizable spaces. And this is still Borel reducible with this ES infinity. So inspired by that result, and that for continua, we started to be interested in the class of rim finite compacta. Rim finite metrizable compacta, right? Because this is a very natural class that contains both zero-dimensional compacta and rim finite continua. Okay, of course, zero-dimensional compactum is rim finite because it has a base with empty boundaries, so especially finite. But actually, it turned out that this class is more complex than this ES infinity. So this ES infinity can be reduced, Borel, into that one, but it is strict. One cannot go back. Okay, so we were quite surprised by that. And this is one of the things I could present here in some details. Okay, so maybe one more thing to note is that there are some possible applications, say, to Banach spaces. Because if we consider a compact metrizable space, K, we can assign to it the space of all real-valued continuous functions on K. And it is well known that two CK spaces are isometric if and only if these spaces are homeomorphic. Okay, and these are Banach spaces. So this actually gives us a reduction from compact spaces to Banach spaces. And for example, the result for continua here, that it is Borel bireducible to this EG infinity, can be translated to Banach spaces, because if we take a continuum here, we get indecomposable Banach space here. Okay, so using that result for continua, we can conclude that indecomposable Banach spaces are still Borel bireducible to this EG infinity. Okay, but I was asking several people and they were not able to answer to me whether, if we consider absolute retracts, this K, and we consider this CK, whether one can somehow express this in the language of Banach spaces, whether these are somehow special. Then it will be just a corollary of our result that some small class of Banach spaces is still Borel reducible to this EG infinity. Okay, so when dealing with these reductions, for us there were some obstructions with the dimension. So a question is whether there can be some Borel reduction of this EG infinity into, say, into the homeomorphism equivalence relation restricted to, say, one-dimensional compacta. So this is what we don't know, and I am usually asking for that in every my talk. Okay, so now I think that I explained the results that we have in this area, but now I would like to explain some ideas. Okay, for
Can you? There's like you said that dendrites is one-dimensional.
Absolute retract. Yes.
So I guess you already know that there's a one-dimensional compacta that's not a dendrite.
Yes, there is plenty of them. Yes. Okay, so I would like to explain here some ideas how this can be done in a very simple way. The original proof is like 10 pages, and the authors are using some technical equivalence relations in between. But I think I can give a straightforward argument for that. Okay, so what I will try to explain is that the homeomorphism relation on compact metrizable spaces is Borel reducible to the homeomorphism relation on continua. So what does it mean? So we need to assign to every compact metrizable space some continuum in such a way that the assignment is Borel. And if we have homeomorphic compacta, we assign homeomorphic continua, and vice versa. If the images are homeomorphic, then the original compacta were homeomorphic. Okay. So, well, the most basic way how to produce a continuum if we have a compact space K is to assign a cone to it. So K times I, or K times 0, 1, and make a quotient where, say, K times 1 is just squeezed to a point. Okay. Well, but this is not working. For example, well, if K is 1 or 2 points, it will give the same, right? It will give an arc. Or if K is an arc or a simple closed curve, again, it will produce a 2-cell. Okay. And I think that there are many more reasons why this does not work. But actually, we tried just to replace this closed interval 0, 1 by some more complicated space. And there is one very complicated space that is called Cook continuum. So a Cook continuum is a continuum C, which it is non-degenerated, so it has at least 2 points. So it follows that continuum many points, such that whenever we take some subcontinuum C prime, and if we take some continuous mapping from C prime to C, then actually phi is either constant mapping or phi is the identity on C prime. Okay, so it is very rigid, this continuum. If we take any subcontinuum here, and we are trying to map it by some phi, C prime into C, then either it has to be to a point, or the image is this C prime, and phi is identity on that. Okay. Well, such a continuum exists. Do you believe or not?
Hard to believe.
Okay, so we will use this tool instead of this 0, 1. So, and we will check that it works, actually. So,
Is it unique?
No. There are plenty of them, especially if you consider any subcontinuum non-degenerated. It is a Cook continuum again. So even you can consider continuum many of them.
Non-homomorphic.
Sorry?
They're always non-homomorphic.
Yes, of course. Even very incomparable with respect to continuous mappings.
In the definition?
Yes.
And they are planar examples or just...
There exists a planar example. Okay, so we will fix some Q continuum, and we will fix some point C in that Q continuum C, and I will erase this. And just for some technical reasons, I will do the following. So I will denote by Q the Hilbert cube. Well, this is not the same Q as here. And Q prime will be the quotient of the product of Q times the Q continuum. And it's a quotient where Q times this single point C is pushed to a point. So this is this quotient space. And I will denote by Q the quotient mapping. Okay, and we will define the reduction F that will actually start in the hyperspace of the Hilbert cube, and the image is the hyperspace of Q prime, and it will be defined in such a way that F of some compact space K that is contained in the Hilbert cube equals to the image under the quotient mapping of K times C. Okay, so it is almost the same as I wrote here. Instead, this is replaced by the Cook continuum, and we fixed some quotient of the whole Hilbert cube. Well, maybe somebody can say that this is not the Hilbert cube, here's this Q prime, but it can be embedded there, okay? So it doesn't matter, and the reduction will be actually okay. Okay, so the picture is like this. So we have the Hilbert cube, say here, and we have this Q prime. This Q prime is actually this Hilbert cube over which we have this cone made using this Cook continuum here. So this is Q prime. And whenever we have some compact set K here, maybe disconnect it, then we assign to this K this cone here. Okay, the image under the quotient mapping. Okay, so it is not so obvious, but it follows easily that this mapping F is in fact continuous. Okay, here by this K I denote the hyperspace of all compact subspaces. F is continuous, and clearly if K and L, if K is homeomorphic to L, then F of K is homeomorphic to F of L. Well, why? Because we just apply the same topological procedure to that space. And of course, the image of F is always a continuum. So for every K in the hyperspace, it holds that F of K is a continuum. So in order to prove that this F is a reduction, we need to prove that if the images are homeomorphic, then the pre-images were already homeomorphic. If F of K is homeomorphic to F of L, then K is homeomorphic to L.
This is where the rigidity is so important.
Yes, yes, yes. Okay, so how do we do that? So suppose that H is this homeomorphism of F of K and F of L. Now I will draw a picture, or maybe not. Maybe we will consider some point in F of K. Okay, so F of K, this is this quotient. So any point in F of K is described by a pair where X is in K and A is in C. And suppose that the image of this point under this H is some point, say, this is some point in L, so Q of YB, okay, where Y is in L, B is in the Q continuum, and X is in K and A in C. And we will suppose for a while that A is different from B. Okay, so we want to prove that A equals B, right? So we suppose for a contradiction that A is not equal to B. So I will draw a picture. So we have this Cook continuum C here. We have this compact space K here. And we have this, say, cone here. So this is this f of k. And then we have this compact space L here, and this f of L here. And we suppose that we have a homeomorphism H between them. And we have these points. So we have this point Q xa, so somewhere here, say, so it corresponds to some x here and to some a here. And we have this point Q of yb, so we have some y here and some b here. Well, and what we can consider? We can consider an embedding of the Cook continuum to this image. Okay. So this will be Ix, and Ix will be an embedding of the Cook continuum C to this singleton X times C. Then we have this H, and here we can consider a projection to the second coordinate of this cone. Okay, so this is a projection to C. And what happens if we consider the composition of these three mappings? So if we apply pi2 to this H and to this I of X. So this is a mapping from C to C, continuous mapping. And it holds that it maps the point A to the point B. But we suppose that the points are different. So it has to be the case that this is a constant mapping. So by the properties of the Cook continuum, this mapping is constant. Okay, so what does it mean for this mapping H if this composition is constant? This means that this whole part needs to be mapped by H to the pre-image of pi2 of this point B. So this part has to be sended by H to that part. Okay. And the image of H of IXC is a subset of Q times Q of L times this P. Well, but this especially means that this top point is mapped to that level, okay? And this point is actually an element of all of these things. So we can go through this argument again, and we obtain that this part is mapped to this thing as well. And this holds for every part here. So finally, what we get is that H maps the whole thing here into this thing here. Okay? So it follows that H is not onto. So something was wrong because we suppose that H was a homeomorphism. So it has to be the case that A equals B. Okay? And what does this mean? Well, this means that the mapping H preserves these levels. Okay, that such a level is mapped to such a level. And every level here is homeomorphic to the K, well, except this single one. And every level here is homeomorphic to this L. So it has to be the case that K is homeomorphic to L. And this is actually what we want. So the proof is simple in this way.
Was there a hint of this? Was there a hint of this argument in what they did? Or?
No, they did completely different things. Okay, we have another construction that is avoiding Cook continuum. It is just using some arc-less continuum, which is much easier to construct. But it is not enough to do it in this way, but one needs to be somehow more careful. One needs to attach something more, and then it works.
What kind of continuum?
Arc-less continuum that does not contain any arc as a subcontinuum. So that's this. And okay, I don't know how much time do I have.
Usually end at 6.
Uh-huh.
Not as much as 24.
Okay, so I can just present another thing, and this is this Borel non-reducibility. Okay, so I said that if we consider the homeomorphism equivalence relation restricted to ring finite compacta, then this cannot be reduced in a Borel way to this ES infinity. So how can we prove this? So we will prove that something is not Borel reducible in such a way that we prove that there is some Borel reduction.
What?
That
made no sense to me.
Yeah, for the first glance it does not make sense, but I will explain it. So there are some equivalence relations that are quite simple, but still they cannot be Borel reduced into that one. Okay. The best for us is the following one. If we consider the Hilbert cube, but now for me it's like sequences of real numbers between 0 and 1. And we consider the equivalence relation given by the asymptotic behavior. So, well, this is a notation from functional analysis, I think mainly. So C0 usually denotes the set of real-valued sequences whose limit is 0. Okay, so by this, I mean an equivalence relation such that a sequence xn is equivalent to some sequence yn if and only if their difference is in this C0. So in other words, the limit of xn minus yn is 0. And it follows by the turbulence theory that this equivalence relation cannot be reduced in a Borel way to this infinite, ES infinity. So for our purposes, it is enough if we prove that this equivalence relation can be reduced in a Borel way into that one. Into the homeomorphism relation ring finite compacta. So again, this is just kind of playing with spaces. So what we want to do, so we want to find...
Is this an orbit relation? Is it induced by group action?
Well, this is not completely a group action because, well, if I replace this closed interval 0, 1 by R, it will be naturally a group action. It will be an orbit equivalence relation. But here, since if I add some sequence converging to 0, some numbers can exceed 1 or be below 0, so.
I mean, it is reducible to E.g. infinity.
Yes,
Yeah.
yes, it is. It is.
It reminds me, I mean, E1, reminds me of E1, which is not reducible for E2. Where you say from some point on they're equal.
Okay, I don't know what
That's
you mean
much
now.
worse. Well, you said the differences converge to 0.
Yes.
And E1, you say it's from some point on they are 0.
Yes, yes. So this is
It's not much
different.
Yeah, but that's not reducible to a root
That's
measure.
true, but they're incomparable.
They're incomparable. But this is reducible to a root action, you see.
Yes, it is.
Even if it's not exactly equivalent to 1. Maybe it is.
Definitely it is reducible
Mhm.
because this is reducible. And I don't know whether it is equivalent or... Okay. Okay, so what we need to do, so we need to find some Borel mapping, and I think that it will be again continuous, that is going from sequences to infinite compacta. That is actually a reduction of these equivalences that are written there. Okay, and of course, since this equivalence relation is written in this way, there is a very natural way how to assign an infinite compactum to it. Okay, so what we do, we consider a sequence xn here, and we assign to it the following compact space. So we consider a segment 0, 1 here, and we consider all these points as points in the plane. So here we have x1, here we have 1, okay. x2, say 1/2, and so on. So this is a compact subspace of the plane. But if we assign to such a sequence this compact space, this segment and this countable sequence that is approximating this segment, then it is not enough. This will not be a reduction because we need somehow to remember the points. Okay, so we need to add some labels. We need to be able to distinguish which one is first and which one is second. So we can add some labels so that still we have infinite compactum. Well, the easiest way is to consider just the number of arcs, right? So in this way, we can label the points. Okay, so now if we have two sequences, xn and yn, and if they are equivalent, meaning the limit of their differences is 0, then definitely we can produce a homeomorphism here that will just map these points onto itself, and it can be extended by identity here. Okay. And if we try to a reduction, so we need to prove that if these are homeomorphic, then these are equivalent. Well, this is not true, because if we consider a sequence of 1/2 here, well, it will give us such a space, and if we consider a sequence of 1/3 here, it will give us a homeomorphic space. Well, the problem is that this homeomorphism on this segment 0, 1 need not to be identity, right? So we need to somehow make this segment rigid. So in this construction, we can do that rigid, we can consider a countable dense set here. And we will attach to the nth points, say, okay, a 2n odd. And here we just use odd numbers, right? 1, 3, because we have countably many labels, so we can partition it. And now it works, okay?
Sorry, what I just couldn't hear you. On the vertical, what are you labeling?
So we have a countable dense subset there, and we can order this set, say we have some sequence of points Pn here, and to the nth point we attach, say, 2n odd. So there are 2n many spikes, and the diameter tends to 0. Okay, so now every homeomorphism needs to be identity on that segment, and then it will work. Okay, well, in fact, we could be a bit more careful. We don't need to attach n odds. We could attach compact countable spaces as these labels. Okay, because we can distinguish them using the Cantor-Bendixson rank. So using this, if we use these labels instead of these n odds, we could obtain a space whose only non-degenerated component is this arc. So it will be a very poor compact space. It has only one non-degenerated component. Okay. And of course, we use this as the labels here also, when these sequences differ by the Cantor-Bendixson rank. So in fact, what we get is not only ring finite continuum, but the boundaries of some basis here has at most 2 elements in this space. So it is even a smaller class than a ring finite. It is like rim at most 2. Okay, compacta.
So what is your conjecture of the complexity of the ring finite?
Well, I guess that it is somewhere in between, but I don't know how to prove that it is strictly below this EG infinity. Of course, with my knowledge, the only possibility how to prove that is to use some equivalence relation for which it is known that it is strictly below. And
you could try to use this observation that you just made about, what did you call it, rim 2 or something? You could try to show rim 3 is strictly above rim 2.
Okay. I will try that.
Right, I mean, that's how some things have been done before, when there wasn't an obvious thing sitting in between, but there's a natural hierarchy, and here it is, at the ends. You just try to show it's strictly increasing.
Okay, thank you. That's a good idea. Okay, so from my side, that's all.
Questions? Where did the word dendrite come from? What a strange word.
I know that it is used in biology for some things.
But who first named it?
Who first named it?
Not in biology, in math.
I don't know. Okay, maybe Janusz Haratonik, but I'm not sure. I don't know. Maybe it is older.
All right, thanks again.
Thank you.